Let's go on to another very interesting and important relation, that is symmetric relation. Now, what exactly do we mean by the word symmetry? Now, symmetry actually refers to a reflective property. To take an example, humans are said to be bilaterally symmetric, and as you can see, uh, if the human body is vertically divided into two halves, you can see that there are it's as if one half is reflected on the other. So that's another thing. Let's get to the key point. The important point here is that in a particular relation of a considering the ordered pairs of two elements A and B in a particular relation, the key point is that if the elements A and B are pairing up to form an ordered pair in a relation, then that relation should also have the ordered pair in the reverse. That is, there should be BA. Now, when in this statement also note the interesting point that if it's the same element forming the ordered pair, that's if it's AA, then the key point is that you don't have to have a another ordered pair as the symmetric pair, because we know that for AA it's AA itself which forms the symmetric ordered pair. So that's an important point. Now, it simply is defined as a relation R on a set A is said to be a symmetric relation if AB has the ordered pair AB being an element of the relation implies that BA is also an element of the relation for all AB is an element of the set A. That is, now we know that we can write the relation as ARB. It implies that BRA should be there for all AB is an element of the set A. Now, what does it mean? Conversely, that is, if you take it the reverse idea, if you take the reverse side, it means that a relation R on a set A is not symmetry if there are at least two elements A and B which are elements elements of set A such that AB is an element of that particular relation, but BA is not an element of the relation. So that's what I just mentioned in the beginning. That is, if AB is present in the ordered pair of the relation, there should be a BA. That is, if BA is not present, then naturally that particular relation is not symmetric. Now let's take a simple example to clear the point. Take a set A consisting of elements 1, 2, 3, 4, and you have the first relation coming up. And as you can see that for every ordered pair AB, there should be BA. So for 1, 3, you have 3, 1. For 1, 4, you have 4. And so if you are asking what about 2, 2, we know that for that ordered pair, that itself is the symmetric ordered pair. So you don't have to write the thing again. So that's the point here. For 2, 2, it itself is an ordered pair. So you don't have to repeat it. That's the key point here. You don't have to repeat the thing to prove it. So that's the key point here. Now, if you look at the second relation, you can see that it's 1, 1, 2, 2, 3, 3, which is okay. But what about 1, 3? Now we know that if there is the ordered pair 1, 3, you ought to have 3 on. But as 3 on, the ordered pair 3 on is absent, this particular relation on set, that is the relation R2 on set A, is naturally not symmetric. So, what are the points? Now, some interesting points are there, and we should be knowing about it. Now, we know that the identity relation, which is the uh, relation as the Cartesian product of the set on itself, and the universal relation, which again is consisting of all relations of the set on itself. So those two relations, that the identity and universal relations, are symmetric relations. Of course, they have to be non-void sets in this. That is, they ought to have elements. So those two relations are symmetric relations, because we know that for those two relations, if there's an ordered pair, naturally the symmetric ordered pair would be present in the relation. Another interesting point is that a reflexive relation can be symmetric, but there's a chance that it is not necessarily symmetric. For example, for taking a set A having elements 1, 2, 3, you can see that if the the identity type of ordered pairs make it reflexive. That is, if the relation R has the ordered pairs 1, 1, 2, 2, 3, 3, then naturally it's a reflexive relation. Actually, it's also a identity relation, but for 1, 3, as we are already mentioned, there is no 3, 1. That is, there's the symmetric ordered pair of 1, 3 is not present, which simply means that that particular relation on set A having elements 1, 2, 3 is not symmetric. Thank you.